lovely people, ladies and gentlemen. Let's talk about the shear walls that everybody seems to be talking about, but nobody quite seems to understand them so far. So let me throw my hand in the hat. To talk to you about these shear walls. Well, the shear wall that failed on the main building, discussing it, it looks like this. That's that. You guys might be familiar with it already. This goes from the basement all the way up. It's about that dimension there, about 17 feet. The shear wall on the structure that stayed, it's interesting. We see that big wall, right? So I want you to think about that big wall. And I'm going to give you something else to consider. So that goes from right here where my mouse is, right to here. This is where we lose some of the structure going out to the front of the balconies. The balconies. This shear wall has a dimension. It's an interesting little dimension. And that dimension is coming up on us now at 54, I believe I recall correctly, 54 feet. I'm going to scroll over. And I'm going to scroll to the right. There we go, 54 feet. It is, take note of these measurements. I'll triangulate them for you in a minute. This is 54 feet. This 24 foot 4 inches is very interesting, the 4-inch part. There's 10, 17, 10, and there's 15. There's 2 inches of cover, 2 inches of concrete cover. So contrary to a lot of people's statement, there is significant cover that they do know how to add more concrete cover. Well, there's this 8-foot step back. 8-foot step back. 8-foot step back. Now this is the part of the building that didn't fail, this part over here. This side, you would have the floor slabs going into the structure. So this is the way it looks like here. So if I were to go to the left a little bit, this would be the cutaway view. If I could look from the parking garage and I could remove part of the building, I would look all the way up. And when I got to the top, I would see what we see left behind. The elevator, the elevator utility room. And that's interesting, a piece of steel there. This is where this should be the roof. This is that came out and failed. If you take note here, you take note that the reinforcement, this is where I said it did a rotation, that when this part of the slab went down, it rotated and buckled the wall right about here in the images that you see of the building, and a triangle's missing to the left. But it buckled that wall out here. And interesting, why did it buckle it and not just lift this all the way off? Well, it turns out there's a beam there, a significant beam 39, and a similar beam 39 inbound. So what is this void here as we're looking at it? These are floors, and this would be the elevator shaft, is the elevator shaft. The reinforcement, these are the beams 38. They're similar. All of them say 2 number 5s top and 2 number 5s bottom. This is the steel. It is an 8x10 concrete beam, and this is the stirrup design, which is saying it's 135 degrees. It's got the 2 hooks back to it, and it's saying use number 3's 8-inch on center, and they say use that from the 3rd floor through the 12th floor. So this is how you make that beam. It says space it 8-inch on center, these stirrups. As you go, that's the 3rd floor. As you go from the 2nd floor through the 3rd floor, it says, well, they look similar. It's number 38, so they will be similar. This is 38. It's going to be the same again, 38, 38. So this one is the lobby area. Remember, on that part of the building, there is no floor 1. There is the lobby area. And there's the lobby. And that was beam 37. Interesting little duck. That one goes down to the basement, the parking garage area. And this is the elevator to the basement roof. They're Basement roof. Basement roof. Well, the basement floor. All right, let's not get caught into semantics on that. 30 times dimes. You have to have 30 dimes to enter the building, or it doesn't work. And dimey. That was what's his name? SpongeBob would say. My first dimey that he made. Anyway, 30 times the diameter rebar from here would be the extension up. So if this is 5/8 rebar, it's 30 times that they want to stick up. And then it would get the reinforcement of that looking like this, all the way up. This is what it looks like all the way up to the 12th floor. The spacing, everything. Now, remember the 8 foot. Let's get back over here. Remember the 8 foot. So this is 8 feet, and this says 17 feet. All right, 8 and 17. So once you remember for a moment, let's zoom out a little bit. 8 and 17. I'm trying out a new mic. This mic is really dialed up, so let's see if YouTube can turn down this much of the volume. Oh, this is the floor level correction. This is the lobby level framing plan. Lobby, it's kind of fast on this mouse. Hold on. Penthouse. Roof level. Okay. We'll just go with the roof. This is the roof level. This is where that floor went down. The lobby went down. This would be K, L, and M. And down she goes. Oops. Doesn't work that way. Sorry about that. Okay. So at that level, this is again the roof level. This is 54 feet, approximately from here to somewhere about here. I know it's got a little more bump. Trust me on it. Let's work on that. Let's slide up. This is the penthouse floor level. And this is that shear wall. Now take note of the shear wall to the right first. Here's the shear wall, just a wall, a flat wall, no back bracing, if you will, no bracing going this way. Huh. Look at this one. It has bracing going that way. How many feet does it go that way? And there it is again. How many feet? Well, did I already give the answer? Did I already not give the answer? And as we scroll up above this one, 17 feet. There's a 17 feet, there's a 10 inch, there's a 10 inch. We're at the basement level, so cars are going to have to go through, or etc. That's a little walkway. So it's a little break, that little beam there I can't find. That's that one at the lobby that we see right now that's left intact after the explosion. They keep showing this wall here, and they show the core samples into it. Well, that is that wall. 80 inches. That's the 8 feet right here. 8 feet, 8 feet. There's 17. There's 20 foot 4 inches. There is 15 feet. (20 feet 4 inches). And as we come down and we look at the shear wall again, so now you understand the shear walls a little bit more. There's your 20 foot 4 inches. There's your 2 inches of cover. There's your 17. Total 54 foot long in that one area there where the wall shifts, where it comes in. And there's a doorway at the multiple doorways or breaks in this wall system at the breaks where the stairwell is right here. I believe the stairwell is right here where you go down the stairs. I think you can see out as you walk on down these stairs. So it's like a beam there, or are the stairs here? I can't quite make it out yet. Anyway, it's kind of insignificant. But what's significant is that this wall, the shear wall, is not as baby cakes as everybody says, or you may think it is, that it's just a flat wall system. It is not. It's a continuous 54 foot long wall. 54-foot long wall. That's the 5-foot door opening, maybe with 5-foot thing. Anyway, 54-foot long wall with these 17 feet apart. They make integral an 8-foot brace, west to east brace. There is none like that here. So this is when this building goes down. It's not that the shear wall did this. This is also a back braced wall system. This is the elevator shaft, I believe. So this is also back braced here with the corners that help maintain why this building can collapse, and why this doesn't get engulfed. Why this doesn't get engulfed. Once these start going, the significant span is 23 plus, what's the balance of this? Here's 23 right here. I believe that 23, well, maybe it's 23 right there. Let's see, zoom in. That might be 23. It might just be a break in the line. So maybe 23 feet from here to here. So when this starts breaking in, punch shearing, this flaps over, and the weight of it and the little bit of engagement of steel that's in here easily pulls out of that wall. Specifically because it was not it was integral only with a couple of the reinforcement was only integral. Well, was integral inside this beam, but this beam is solid all the way up. It's a solid wall all the way up, and it's got this back bracing. So it gets tugged on, not all at once, but it gets tugged on one floor at a time, so it can handle that reaction one at a time. It wasn't like this whole thing shifted to the right and it had a big tug on the entire wall system. So now you see why this shear wall is totally, on a different level than this shear wall. It's a little 17-foot straight wall. 17-foot straight wall without this back bracing, if you will. This 8-foot all the way up through the floors. This is a short video, but I wanted to give you more data on why this shear plane was created, why it didn't fail. And here's your hooks. They go into there. It's a 12-inch wall. The hooks are whatever, number 4 rebar. The radius determined back in 1981 might say, 6 times the radius of the rebar to make the hook. Something like that. There's whatever it was in 1980. I don't know it to be 6. I'm just saying that. Could be 10 times. And there it is here. This one says use number 5. And over here, this is at the balconies. Remember at the balcony, it tore apart. At the balcony, this is the penthouse. It tore apart a V shape out of that wall there. And that V shape is, well, it's because these are the rebar, the reinforcement. The 5 number 4s. And then over here, it's just the 410. Number 4 is 10 inch on center. So it's able to disengage itself with that little, see how it's inside there? So it's interesting though, they're showing hooks. And I don't see blowouts like that at that wall. This hook goes, it'd want to blow out that little piece of a cone that's inside of it. I should have zoomed in, not out. So it would want to blow out that cone. It would want to blow it out. Zoom in again. Okay. It would want to blow out this section here, like little blowouts, but apparently it looks more like this. And in fact, we saw on the 8th floor the transition. The slab is still in place. Speaking of 8th floor, while we're here, so we zoom out, and I'll wrap it up with that. Not to be confusing you with too much data, but speaking of 8th floor, zoom out again. The transitions take place at the 8th floor. And it would be here. 8th floor through 12th floor. Still beam 38. Hold on. Right, now this is beam 38, 8th floor, 8-inch slabs. Sorry, I'm turning around the chair, so if you hear noises, it's my chair. There's an 8-inch slab. The 8-inch slab. The basement has a 9-inch slab, which we know. And this is interesting. Is this also the basement roof? Is this the parking area they're referencing right here? This is that one's interesting. Little ducky. Okay. So to give you one more on that before I wrap up the video, let me see if I can find it. The significance of the transition. All right, so zoom out. That's that shear wall that's 17 feet. The one that right here, that's a smaller one now. Now, it is 12 inches thick. Moving over, hold on. I guess I should have talked. This is also 12 inches thick. But this now has that 10-inch return, 8 foot back, with reinforcements and rebar that's tying it in all the way out. Okay. So I thought I'd give you some detail on the shear wall so you can understand as I put this together. My pull-out test, I have reasons for it. We'll get to it. Those are, I want you again to think of rebar as the screw or bolt, if you prefer, and the nut is the concrete that it's got to tie into. And sometimes a screw, if you try to hold a deck on and you only use a 2-inch screw, it goes 2 inches into the wood, into whatever you're trying to tie it into, it's not as good as going 12 inches into the wood or whatever we have. Well, remember we have a transition at the 9th floor. We transition, 8th floor, we transition to smaller reinforcement. Smaller reinforcement and less of it. There's more below at the floors below. So when the rattling takes place, vibrating up this deck are bolted connections, and that would be the rebar into the columns. With the lack of cover, makes it an easy pull-out. Remember this though, the path, the load path. Let me see if I can do this right with this one. So, all right, yeah, I'm trying a different computer out to see if I can use this system, and maybe I can. So remember our load path goes like this. It's supported, braced there because it's not just out in space. And then comes across. And again, not supported in space, so there's a column there. Hey, I'm watching that Dexter show. Dexter and from England or something like that. Oh, Dexter's a naughty little character, isn't he? Oh, he's more naughty than I am. All right, so here's our load path. So so if you get to pick your poison, remember this is 1'6" elevation, so it's like that. But over here, there's a 7-inch, I believe, 7-inch deck, and then 7 inches here. See, 7 inches. Oh, it won't let me zoom for this one. This is definitely, I'm not sure what I think about this. All right, I don't know how to undo. I'll have to work on this. But this is the true load path. And so if you imagine if you get this to fail, there's the driveway, right? If you get this to fail, you automatically getting some of this to fail by default, just right up to that drop slab. There's the video camera coming this way, right? So Oops. Oh, God, beautiful. So there's the video camera shooting down here, and if you get this to fail, it seems like you'd be able to get send backwards. Let's try it. That did nothing. It seems like you would get, if you get that to fail, it seems like you'd take out that upper deck too, all the way over to the transition. Well, wait a minute. The transition's back here where it changes elevation, and then there's 7 inches right there, the step down from inside here. So this would still leave that. So here's our 11 foot 10 right here, 11 foot 10 where my hand is. This is all 1110, but then this says 1110 there. Let me get the zoom character out if I can get this to work. Magnifier. That says, yeah, 12.9. There we go. Oh, it's 11 foot, the distance, right. So the elevation there is 12.9. That's a difference of 100 feet. I'm being smart because I couldn't get the calculations fast enough. So it's 11 inch step up. And then there's another 7 inch right there by the hand to get inside this new elevation of 13.4 right there. So you've got a couple of steps before you get to here to get this to failure. But, you know, I've seen the models. You know, I saw the models, and everybody has it going down to the ground. This is the only one that appears to go all the way down to the ground. This is the only one that appears to go all the way down to the ground. If we look at the planner, we have a planner box over here. This planner box doesn't look like we're looking at ground level there. Very interesting, though. Very interesting, because we see if planner box is here, and we see the deck, but then we see this the structure kind of hiding, you know, by chance, hiding part of our deck where we'd want to see the deck. So the deck is here, and this is what we're going to talk about. These next video, we're going to hit on these columns and triangulate from these columns here that we can observe how much of the deck is flat based on tile cracking, etc. And then we're going to, and this decking is good over to here. So that's the pool decking we're looking at. So keep in mind, if this collapsed, when this video shows, how much of it can we overlay like this? Well, we see the planter box up here, and we see some tile. We see the tile, like, you know, all of this is visual tile all the way over to the planter box. It's visual tile work, which means we're looking at the deck. So where do we see the rotation is the question. I'm going to get to that in future videos when I learn this software. But right now, this was to show you about the shear walls, give you some target to start looking for and start learning. Get ahead of me if you like, ahead of the videos, and test out this mic. All right, I'm gonna load this up now.